And in this episode, we're going to look at the noise that cars are producing and the problems or challenges we have with it, be it on the racetrack or be it on the public roads. Noise regulations are becoming more and more tight. The days of open tailpipes are long gone. And nowadays, if you get to the racetrack, you are constrained in some cases to 98 decibels or even 95 decibels, which is really a big issue. And like in my case, if you don't adhere to it, not deliberately, then you get black flagged. Like in my case, it happened a couple of times, and if you get twice a black flag, your day is finished. But the same thing goes for road cars. I don't know where you live. Where I live, we actually have even noise cameras. We all know the speed cameras, but the noise cameras will flash you when your car is making too much noise, specifically those cars with clack boxes. So we have a challenge. We want to stay within the noise limits, but at the same time, we don't want to compromise the performance on the engine. And in this video, we'll be looking at multiple topics. The first thing we're going to look at it, what are the noise sources of a vehicle? How is it measured? And what is the unit in which we measure? In other words, the decibel. We give an explanation on the decibel and how we are perceiving sound. And then we're getting into the methods on how to cancel noise. How do we reduce the noise? And for that, we will be talking mainly about the exhaust system, the mufflers. We will address two types, the reactive one and the absorptive one. And that should give you a pretty good insight on what you can apply to your car, be it a street car or a race car, to reduce the noise. The noise sources can be classified in four major areas. The first one and the most important one is engine noise. The second one is transmission noise. That includes the gearbox, but also the drivetrain and the tires on the tarmac. And then we have the aerodynamics. You may have some air noise coming from that. And then finally, we have what we call vibrations of the body or whatever is in the car. There is no doubt that the engine is making most of the noise. But even within the engine, we have different noise sources. The main source is, of course, the exhaust. And that is because we have these explosions inside the cylinders, and that is causing pressure waves which are going down the exhaust pipes, the header, and down into the exhaust, and then through the mufflers to the back or the side of the vehicle. And that is making quite a lot of noise, and we will get deeper into that. The carburetor, especially with trumpets on, is going to make quite a bit of noise. You can solve this with an airbox around it, but then you're constraining the airflow unless the airbox is very well designed. And then finally, we have the valves and the push rods and all of that, because they are also making some noise. But again, those will not be the issue for you racing on a racetrack or on the public roads having too much noise. The main issue will be your exhaust. As you have seen, the engine is quite noisy, and there's a couple of things we can do to reduce that noise. First of all, on the carburetor, we can create an airbox, but building a proper airbox is not all that easy without actually affecting the performance of the carburetor. That will actually reduce the noise. The second thing we could do is having an aluminum valve cover, which is going to dampen a little bit the valve noise, but of course the valve noise is not the main thing. The main thing is actually the exhaust, and that's the one we go into control. and try to reduce the noise level or increase or even change the tune of it. But first of all, we need to figure out on how we are going to measure the noise level, and that is why we need to talk about decibels. We know that the combustion of the engine is making most of the noise, and therefore we could actually calculate what frequency it is, because that's going to become important once we go into do the noise measurement. So to find out what the exact frequency is of your engine, we're going to look at the first harmonic or the base frequency of the engine at a certain RPM. And to figure that out, there is a very simple calculation for that. So the frequency equals rotations per minute divided by 60, which gives you seconds, multiplied by 2. Now, why do we multiply this by 2? Well, on a 4-cylinder, 4-stroke engine, we have 2 combustions per rotation. Let us take an example where we are running 1200 RPMs. We divide it by 60. That gives me 20 RPMs. And then I multiply it by 2. And that gives me 40 hertz. And if we run at 6,000 RPMs, we divide it by 60. That gives me 100 times 2. That is giving me basically 200 hertz. So what we just calculated are the base frequencies of our engine depending on the RPMs. However, there could be some harmonics. The second harmonic would be twice the frequency. And it could be that there is a resonance between the inlet and the outlet of the engine, and in that case, it could become even more dominating. Now, why do I talk about frequencies? Because that is going to be important once we start measuring the noise level. Because at the end of the day, it is how we as a human experience the noise. And the matter of the fact is that we don't hear low frequencies all that good and high frequencies. We are pretty good in the mid-range of frequencies, but not on the lower range. So in essence, you're going to need more power to be produced on the higher frequencies and on the lower frequencies for us to hear it at the same level as the mid frequencies. But maybe I should also explain a little bit what sound really is. If you're looking at your hi-fi at home and you look at your speakers and you play a good song, then you will see the woofer or the speaker, the membrane going back and forth. And when it comes forward, it's creating a positive pressure wave in the ear. When it goes back, it's a negative pressure wave. And these are like waves traveling through the ear of different pressures that are getting into our ear, and there it will cause some vibrations and we will hear that sound. This is how magic that is. So pressure waves are measured in micropascal. This is a measurement for measuring actually how much pressure there is in the wave. So decibels, sound pressure level, this is what we're going to measure in. This is the unit we're going to complicate it, but it's not really. So a whisper is about 30 decibel SPL, and then 140 is about the sound of a jet engine. Now, per 10 decibel, we need 10 times more power. So keep that in mind. So our engine is running, we have the combustion inside the cylinders, and the combustion is going to create pressure waves, which are going to travel through the exhaust system and then be dampened by our muffler system. And we'll talk about the muffler system later. And then finally, this pressure wave is leaving the exhaust, and this is where we go in to measure with a dB meter or a dBSLP meter the actual noise level that the car is producing. Typically, we do it to a certain distance from the car and under a 45-degree angle. 1 meter is quite common. I've drawn a curve here on the board which is reflecting the sensitivity of a human ear. On the bottom line, I have frequencies, and on the vertical line, I have my decibels in sound pressure level. Let's call it power for now. If we want to hear every frequency along the line, starting at 0 to 10 kilohertz, one frequency at a time, and we want to hear this, all of them, at the same level, the same volume, then something has to happen right here on the power level. In other words, if I'm listening to a 10 hertz frequency, I'm going to need about 80 dBSPL. However, if I listen to a 1 kilohertz or 1000 hertz signal, and I want to experience the same level or volume, then I'm only going to need 30 dBSPL. So you see, this is a huge difference. And the same thing is happening at 10 kilohertz. If I would listen to the signal at 10 kilohertz, I would need about 75 dBSPL on the power source. And that's just because our ear is having this specific sensitivity curve. And that is why we go into apply a weighted curve on any noise measurement when it comes down to vehicles. And it's called the weighted A measurement. You don't want to do the C, you want to do the A, because A is how we as humans will hear things. And now we need to talk about decibels, sound pressure level. We kind of talked about on how the engine is creating pressure waves through the exhaust system. And these pressure waves are being generated by the combustion in the cylinders. And the more powerful the engine is, the higher the compression or the stronger the explosion is inside the combustion chamber, the higher the pressure wave will be in terms of strength, amplitude. But also we know that the frequency is changing. So that is why we have a certain calculation that has been set up to calculate the decibel SPL. The human ear can hear a tone of 1 kilohertz at its lowest threshold of 20 micropascal. So if that pressure wave comes in your ear and it's at least 20 micropascal at 1 kilohertz, we might just be able to hear it. And if you've been taking a hearing test, you probably know that's the kind of thing they refer to quite often. To calculate the dBSPL, we need to take our measured pressure, and we do this with a level meter or noise meter, and a microphone works on pressure just like we do, and we divide it by the reference, and the reference was our 20 micropascal right here. And then we take log 10 of this and we multiply it by 20. And why do we multiply it by 20? Well, because the power is proportional to the amplitude squared. So this is the formula which is used to calculate the dBSPL. Now, once we have that formula, we go into apply on top of that the A-weighted version. And remember, I talked about this before. This was this curve I've shown you on how our human ears are hearing or observing sound. So that is the measurement we're going to do. We will measure the dBSPL and we weight it with the A curve. So now we have two elements, the frequency as we discussed, but also the sound pressure level. And those two go together, especially on the human ear, because the human ear is sensitive to a certain range of frequencies and less sensitive to the low frequencies and the high frequencies. And that is why we're going to need to apply a specific weighted curve whenever we do a voice or noise measurement. So if you're on a racetrack or any other inspection where they check the noise level of the cars, then you got to make sure that they do measure in dBA. Then they are using the human weight curve for the ear, otherwise it's not accurate. Because after all, the whole purpose is to make sure that the neighbors on the racetrack or on the road, if that's what the case, are not annoyed by the noise level. So if you want to measure the noise on your car, well, then get a noise meter. They come in all kind of costs, very cheap ones up to very expensive ones. The expensive ones Well, they are very accurate, and those are the ones I would really rely on if you want to do accurate measurements. They probably start around $500-600 or euros for a good one. Now the cheaper ones, even the ones for $40, $25, and $30, I would not buy because they are not very accurate. You might as well download a free app for your smartphone and use it on your smartphone. It's going to be as accurate. But of course, this is not as accurate as a real noise meter. So let's have a look what the app that I have, and it's not a commercial for it because I'm not even going to tell you which one it is, but I'm going to show you on how you can set it up, and let's do a measurement on this car and see how that goes. Here we go. And you can see we have settings on it. And I'm going to use the internal microphone, and I'm going to use the standard measurements, which is all right, which is the NOSH, that's the standard. And the frequency weighing, which is the important part, this is actually set to A, as you can see. And A is what I just explained on the board. So it's reflecting on how we are hearing the sound. So there's going to be some attenuation applied on the measurement on the lower and the higher frequencies. So I have my sound meter set up. It's about a meter away at 45 degrees from the exhaust. And I'm recording it. So let's start and see what it gives us. I'm going to crank it up to 1,000 RPMs and then 3,000. So this is 1,000 RPM and we're having about 85. I'm going up in RPMs now. So you've seen the different values at 1,000, 2,000, and 3,000 RPM. So during that run, we had a L max of 98.3 decibels. As you have seen, a simple app can do already quite a bit, and it's very helpful. Now, my setup was not perfect. I'm sitting at the gateway or the door of the barn, which is not the perfect place to be because you should be in an open space to do this, and then you should have a certain distance as well, maybe more than 1 meter from your exhaust, but it gives you a pretty good idea at least. If those of you that want to do professional measurements, well, then get the proper tool and set it up in the proper environment. There's always guidelines on that on how to do it. But now it's time really to talk about what can we do to the noise level. If it's too much, what can we do? And for that, we need to talk about muffler systems. In essence, there are two types of mufflers. There is what we call the reactive muffler, which is this one, and we'll have a closer look in a few minutes. And there is the absorptive muffler. So this is our reactive muffler, and I already have it cut open so you can have a look inside. What you can see immediately is that we have a couple of chambers. And the principle of this kind of a muffler is that while the gases are coming into the muffler, they're going to bounce back and forth in these chambers. So when we have a pressure wave coming in here, it's going to get along this tube here. Some of it will escape through these little holes here, but then it's going to bounce back in this chamber, but also some of the pressure wave will continue in the second chamber, and it's going to bounce back on this wall, back to this one, and as such, it can cancel out other pressure waves. So if the reflected pressure wave is of the same amplitude or strength and the same phase and the same frequency, then it's going to cancel out the incoming pressure wave. So of course, both have to be the same. So that is pretty good. This is what we call actually noise cancellation. So it's going to come in, some of it will come in this chamber, and this is what we call the resonance chamber. So this is where things will cancel each other out. Other parts of that pressure wave will actually reside in here, start bouncing around, maybe do some cancellation, then getting out through this hole here, and then actually getting back into this pipe right here, and then on the way out. Now, as you can notice, this is a very restrictive setup. You know, the Exhaust gases, they are subject to a lot of barriers, so it has to travel along and then come back in, and you see all these little holes here. This is where it has to get through. So that's going to cause a lot of back pressure, and you don't want to have back pressure really on your exhaust system. You want to get rid of those fumes in the cylinders as soon as you can and as fast as you can, because back pressure will also result in poor performance, because you're not going to have that suction pump effect with the valve overlap. So really, for a performance car, these are not the best mufflers at all. Reactive mufflers are pretty good for saloon cars and daily drivers because they are very effective in reducing the sound. Now, some of them may have some additional packing inside, and we'll see that on the next muffler. So for me, this muffler, yeah, it's great, but not for a performance car, not for a race car. It's great for a daily driver because it's going to dampen the sound quite a bit, but it's going to have a side effect on the performance. Now I know you can buy some of those that are more tuned to performance engines. So again, if you buy one off the shelf, a standard one, it's not going to be very good for the performance of the engine. No, how much is it going to change in terms of horsepower on the engine? Well, it could be 8 or 10 horsepower. It all depends a bit. But let us look now on the next one. And our second type is the absorptive type. Typically they are round like this. You can see they come in different lengths, and of course the longer it is, the more dampening you're going to get. But let me show you what's inside. In principle, you can actually look through these because it's a straight tube. Now that means that we have almost no back pressure. So these are ideal mufflers for performance. There is as good as no back pressure. Whereby on the reactive muffler, we are having lots of back pressure. Also, they are quite a bit smaller in most cases, so we are saving weight and space compared to this one. So let me show you what's inside one of these. So this is a cutout. We have the central pipe, and this is the central pipe, which is going straight through the muffler. So the gases will flow like this, and they will actually escape this pipe through all these little holes. So the pressure wave will be reduced because the waves can partially escape through the holes. Now, there is a certain percentage of holes you have to have, and I believe they have to be at least 20 or 30%. Now, on this one, it's a lot more. Then, when they escape through the holes, they are ending up in this insulation kind of material. Now, this could be fiberglass, or it could be any other kind of material like rock wool, which is have a high dampening issue. And the pressure waves are converting to heat. So this muffler is going to create a lot of heat. And this is the way you can actually reduce the level of noise generated. These are having one big advantage. They work on most or almost all frequencies, and they are quite efficient because they don't create back pressure. However, over time, this material will disintegrate, or you get carbon particles inside, and the efficiency will slow down or go down, and therefore the noise level will increase. Of course, the whole design depends on the width of the muffler on the outside, but also the size of this tube, the amount of holes, and what kind of material is inside. So let me put this aside and show you what I have. This is one that I have on my cars, and this is a very short one. And I'm using this one, and again, it's a absorptive muffler, and I'm using it on my Formula Fords because it delivers sufficient dampening and almost no back pressure whatsoever. Now, there are situations whereby you really have to get less noise, and then I'm using this longer one here, which is about, well, let's say 1/3 longer, and I'm also putting a corner on the back, so I'm deflecting the waves towards the ground. So this is giving me more reduction on the noise than this one. And you can play with this. Of course, you can extend them if you want. and make it as long as you want or as wide as you want. It's going to be different in terms of dampening. But you really need to try this out on your car. So if you're having problems with too much noise on your race car or your track car or whatever, or even your street car, and you want to keep your performance, get rid of your reactive muffler and go for an absorptive muffler of a certain length and diameter. What we haven't talked about is the size of the pipes. This is a 60 millimeters, I believe, and the wider the pipe is, of course, the better, because then you have less back pressure and you may have a better flow. But there are calculations on how the size has to be calculated for your specific engine, and how the collectors or the exhaust pipes, or the header as we call it, has to be formed with equal lengths and so on to have the optimum flow inside the exhaust. But that's stuff for another video. But now let me show you when we put these mufflers onto one of my Formula Fords and see what the difference is between the short one and the long one. So here's our setup, our Formula Ford with a Pinto 2-liter, and then in the back I have my noise meter, and it's about a meter away and about 45 degrees. And the first test we're going to do is to run it without any muffler. So bare pipe. So let's start the engine. I'm going to rev it up to 1,000 and then 3,000 RPMs, and we'll watch the dB meter. So right now we are running on idle about 1,000 RPMs. And you can already see that we're running close to 90 decibels. So I'm going to give some throttle and see what happens. So this is the small muffler. All right. I'm not going to tie it down completely. And let's see what we have. So let's start it again and do the same thing. We're now running at idle, and I noticed that we are about 4.5 to 5 dB less. Let's crank it up a bit. So this was at 3,000 RPM, and you could see that the noise level was a bit reduced with about, I think about 4 or 5 decibels, but we check it out later on in post-processing. Now let me put up the bigger muffler. And you can feel immediately the heat being developed on these mufflers, and that is because the pressure wave is being converted to heat inside the insulation material. And here she is. And on idle, we got something like 85, something like that. So let's rev it up. So that was it for the bigger muffler. So folks, we are nearing the end of this video, and what I've tried to show you is that placing a absorptive muffler on your race car is better for performance, less back pressure than a reactive muffler. I've shown you the difference between the short one and the longer one on this race car, and no muffler, and we'll review this now together in post-processing. So here we have the results of the measurements we've done. And of course, I've done it inside the barn. I shouldn't have done it. I should have done it outside. But nevertheless, all three measurements were done in the same conditions, so that shouldn't matter really. So without a muffler, we were having about 88 dBA at 1,000 RPMs and 105 at 3,000 RPMs. As soon as I placed a small muffler on, the dBA value went down with about 3 decibels between 88 down to 85, and it went down with 8 decibels at 3000 RPMs from 105 to 97. And then finally we placed the 1/3 larger muffler on, and again we had a -1 dB additional loss at 1000 RPM, so we ended up at 84, and at 3000 RPMs we ended up with 95 dBAs. So that really confirms what I have been experiencing at the Racetrack in Zolder, where I always had an issue, and that is why I placed a larger muffler up, the 1/3 larger, and I was able to complete that event without getting black flagged. So that means I stayed below 95 decibels. Now, of course, on the Racetrack, they are measuring from a long distance along the side of the racetrack, but of course, we also are having higher RPMs. So folks, I hope that you enjoyed this video as much as I did, and I might do another video on how to calculate your exhaust in terms of diameters of the pipes, but also on how the headers are connected and the length of the headers into the collector and so on. Thank you for viewing, and I'll see you in my next video. Bye-bye.